Yes, I participated in this exam. I was one of 3 people who actually passed this thing, so I'm pretty proud of myself. A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians, welcome back to another video. First things first, the brand new, most beautiful equation mathematics merge just dropped. Check it out, link will be at the top of the description. Welcome back to the extremely hard exam series here on this channel. Yes, you heard it right, I said exam this time, so all your spammy comments down there had some impact on me pronouncing stuff. So here you go, you have won, guys. So guys, you did it. By the way, if you have an exam with an extremely high failure rate at hand, make sure to send it to me using the email address at the top of the description, and I'm going to make a video out of it. Here's the basic structure of the video yet again. At first, I'm going to tell you the background of this exam, how many people participated, failed, etc. Then we are going to go into the main exam, and at the end I'm going to tell you the reasons why so many people failed in the first place. And one more side note, the title of this video is absolute clickbait because in actuality only 95.3% failed, but I'm a bit of an engineer myself and I know how to use the seeding function for clickbait purposes. So here you go, 96% failed. So here's some background information on the exam itself. Overall, 57 people participated in this algebra and arithmetic exam. This right here is the original version. For those algebra and arithmetic exams, there's a basic structure. First exercise is going to be group theory. Second exercise is going to be ring and field theory. Third exercise is going to be something to calculate. Something with extremely huge powers, so using the Euler-Phi function, something with geometric numbers, diagonalization, system of congruences, etc. And the last exercise is something really random, and this last exercise is everyone up each and every year, so most of the time no one gets any points there. On my exam, yes, I participated in this exam. I was one of 3 people who actually passed this thing, so I'm pretty proud of myself. No one got any points here, and it was the hardest thing ever put on an exam in algebra and arithmetic in all those 30 years of the professor being there. Now you might ask yourself, what kind of people have to take this exam? It's an abstract algebra exam. Most of the time only the real math boys have to take this course overall. Here it's the case that if you study mathematics and something else and want to become a teacher, so doing pedagogical studies overall, you have to take this exam. And this is one of the reasons why so many people failed, because most of the students suck balls when it comes to mathematics and they just don't understand shit. They only understand how to add 1 and 1 together. No, not even that they do understand, because they have no idea what the Peano axioms actually are. But yeah, that's the demographic of people participating in this exam. And now we are going to take a closer look at that. Let's see what the exercises actually are. You can find the exam down there in the description. The original one and the English version that I have transcribed for you guys. Like mentioned before, the first exercise deals with group theory, and here we are having an easy exercise about matrices. At first, we have that there are 2 groups, U and V, which are being generated by those matrices out of the GL2 set free, meaning we are going to do modular arithmetic, meaning the elements that we are going to have there, so like in the entries, are 0, then 1, and then 2, and if we have 3, for example, this is the same as 0 in our modular arithmetic. Then there comes 4, this is nothing but 1, and so on and so forth. Now that you are familiar with modular arithmetic, let us go ahead and take a look at the first exercise. So at first we want to show that UV, so U times V basically, is a subgroup of the GL2 set free with 8 elements, and that W being generated by A squared, so this matrix squared, is a normal subgroup of UV. So at first what you want to do is to find out the order of those 2 matrices A and B. Order means, let us go through an example. if we have the identity matrix, for example. No, or let us take a look at 0, 1, 1, 0. That's a matrix. Let's call it, I don't know, eta. And if we multiply eta by itself, so eta squared, it's going to give us, okay, this is going to give us at first 0. If we 1, I'm terribly sorry if we put it on here. So those two multiply together, 1, 0, 0, and then 1 in the last entry. Meaning overall, this right here is just yet again the identity matrix, meaning the order of eta of this matrix that we have right here is 2. So the order of eta is 2, because it takes us 2 powers basically to get back to the identity of this group or this matrix in general. Meaning we have to find out the order of those two. The order of those two is going to be 4. So the order of A is equal to the order of B is equal to 4. Just keep this in mind for now. So this is just straight through calculations. Also, U and V are both subgroups of the GL2 set free, just because all elements in here of U and V are actually invertible, and all the entries lie in set free yet again. Makes it a subgroup yet again. So okay, U and V is the subgroup. How can we find out something like this? Well, for U and V being a subgroup, we want to see that we can express UV as the generated group by A and B. For this, we need A and B, both orders, to be finite, and we need to show that there is this certain property that holds, namely that A times B is the same as B times A to the k power for some k out of the integers. Okay, this is something that you have to show, and if you are able to show this, then we have that this holds, all elements in here are going to be invertible yet again, making UV indeed a subgroup of the GL2 set free. So if you've ever done abstract algebra, this is kind of a basic exercise. Now we need to show that UV has 8 elements. How can we show that it has 8 elements? Well, obviously using Lagrange's theorem. Daddy Lagrange, one of the most beautiful big boys out there. It's one of my most favorite identities. So in order for us to use Lagrange, we are going to take a look at the order of UV, and it can be expressed by the order of U times the order of V divided by the order of the intersection of U and V. This is just Lagrange's theorem. Up here, we are going to have U and V, both have 4, this gives us 16 over, and finding out the intersection of U and V is pretty easy. It's going to be 2 elements, namely two elements, namely the identity matrix and A squared, which is the same as B squared. So this thing has order 2, makes 16 over 2 is 8. If you wish, I can calculate through this exercise in a separate video, so just let me know. So this basically covers this first part, okay, only takes a few minutes. Basically, overall you have 3 hours for this exam and 48 points overall, and you need 24 points to pass this thing. Now, W is a normal subgroup of UV. So normal subgroup is basically just kind of an algebraic structure, and we need the left and right cosets to be equal, so the number of left and right cosets. If I'm not mistaken, please correct me if I'm wrong, or maybe there's an annotation there. So W equals to the set being generated by A squared. Don't forget, A has the order of 4, meaning A squared has an order of 2. It just makes sense using the rules of exponents. Meaning overall, W has 2 elements in there, so this is what W consists of, 2 elements. And to show that this is a normal subgroup, what you can do is you can just go through the regular property, namely that we need some G times N times G being element of W yet again. So for all N in W and all G out of UV, we need this to hold. Also, it must be a G to the -1, so the multiplicative inverse, or the inverse under the operation we are using. Or you can show that W is indeed the center. This is what I did, and this was basically the trick behind all of this. Now, the factor group of UV and W and the line 4 group, we need to show that those are isomorphic. So the first thing we need to do is to show that they have the same cardinality, meaning they have the same number of elements in there. Line 4, as the name would suggest, has 4 elements. Now we need to show that UV factored by W also has 4 elements. So the factor group, the number of elements in there, can be calculated how you would expect it. This is something like UV divided by W. Okay, UV divided by W basically means the order of UV divided by the order of W. I have said that W has exactly 2 elements just because of the power of A, meaning overall, let me see if I can get it on camera. Right, this gives us 8 divided by 2, meaning this is 4. Overall, the order of the factor group is equal to the order of our line 4 group. This is good. And for the line 4 group, you need to show that it's isomorphic, that our factor group here is indeed cyclic. Yeah, this is all you need to show for the first exercise. Just takes a few minutes, at most like half an hour at most, and you can get 12 points from it. It's a pretty easy exercise. Next up is a ring theory exercise, and this one was especially easy just because we have this extremely simple polynomial here at hand. Seriously, this is like finding an enchanted golden apple in Minecraft. This is just a blessing of God. This exercise takes only like, I don't know, 30 minutes or so, and it's so damn easy. So at first we need to show that R, the set that we have right here, is an integral domain in regards to the regular addition and multiplication of polynomials. This is really easy to show. All you really need to use is the subring criteria, okay? Show that R is a subring, just takes a few minutes, really easy. And also you need to show that the identity element with regards to the multiplication, so a 1 is element of what we have here of R. It's both really easy to show, really doesn't take too long. Then you need to show that I is an ideal in R. Well, just go through the ideal properties. So you just need to show that it's basically an additive subgroup, and if you multiply an element out of the ring with an element out of the ideal together out of this set I, then it's also element of I yet again, making it an ideal. Really easy stuff. Now we need to calculate the group of units of R. This is also really easy to do. So my main idea here was that we are going to take 2 polynomials out of here, out of this R, let's say t of x, and multiply it together with s of x. Then we are going to get a whole bunch of stuff, x to the nth power. So those are all coefficients plus blah blah blah, up until something coefficients x to the first power. And overall, this is just some combinatorics multiplying together stuff. We are going to have those elements out of Q. Let's say the first one is A, and so for t of x, and the second one for s of x is B. Overall, you are going to have this this y-intercept, basically, if you interpret it as a graph, being just A times B. We are going to set all those equal to 0, all those coefficients before all the x's, meaning that we are going to have our AB here, and we want this to be equal to 1 for us to calculate the group of units. Now AB being equal to 1 also implies, if we are in a field, for example, or in this case in an integral domain, okay, this implies that A times B is not equal to 0 for all A and B out of Q that we have right here. This only holds if A and B are element of Q without 0. And this just means that Q without 0 is also our group of identities. Group of units, I'm terribly sorry. So this is just some playing around, it's really easy exercise. And for the last one, we need to show that is g of x in R a prime element in R of x, then g of x will also be 1 in R. You just go with this using a proof by contradiction. I was being stupid there when I have written the exam. I wanted to do a proof by contraposition, but I failed miserably because what I did, if we have a statement P implying Q, well, I did a really nice proof by contraposition, namely I said that this is equivalent to not P implies not Q. Well, I was a genius there, don't you think? Failed miserably. How does that come? I wonder. Now, most students actually got a few points on those two exercises, but here is where everything started to collapse. This is a diagonalization exercise and it doesn't look like one because, well, there's not really explicitly some matrix given, and this is what many students up because, well, they didn't know what to do here. So meaning half of points, because no one was able to do the last exercise, half of all the points that you could possibly get went to waste because nearly no one knew how to do either this or that exercise. And if you then had just one little mistake up here, which could happen pretty fast, then you would fail already. So one of the big reasons was this exercise, and I was the only one who actually got a lot of points there. I got 11 out of 12 points because it's so easy and I do not understand why no one got it right. Now, we would like to draw this matrix at first, just to get a feel for it. What we have given here is a matrix A, and I'm going to draw like 4 by 4, okay? Because the dimensions are always even, so we want an n by n matrix here. Let's draw a 4 by 4 matrix. It's of the form 0, 0, 0, and then we have 1 on the not main diagonal basically. And yeah, if you understand how this system works, you could also already get some points because you have to draw this matrix for A being equal to 6. For n being equal to 6. So yeah, pretty easy stuff to be honest. This is how the matrix is going to look, and in general it's going to look like this: 0, the 1, 1, 1, 1, 1, and all the other places are just 0. Okay, I hope you get the gist of it. Now, we need to show that the rank of A plus the identity matrix is n over 2, which is the same of the rank of the matrix A minus the identity matrix. That's really easy to verify, to be honest. So what does A plus the identity matrix look like? Well, this is nothing but, well, we have this weird cross, and do not forget that we have an even number of dimensions, meaning overall we are going to meet in the middle with a block of ones, okay? This is what the matrix is going to look like, okay? And all you really have to do now is just use Gaussian elimination basically on this matrix, meaning we are going to subtract this last line from the first line, this line from this line, blah blah blah, up until the middle, leaving us overall after n over 2 iterations with a matrix that looks like this: 1, 1, 1, 1, 1, 1, and then all the other stuff is just 0. Meaning overall, the rank is just half of what we had before. So the number of rows is just half of what we had before, meaning the rank of this matrix is going to be n over 2. Same thing goes for A minus the identity matrix. Just puts negative signs here, and instead of subtracting rows, all we have to do is add rows together, and then we basically land at n over 2. I hope this is clear now. It's a really easy exercise, to be honest. Next up, we need to show that A has eigenvalues positive and negative 1, and that A is diagonalizable over Q. So at first, we need to show that it has eigenvalues of plus minus 1, and this just has to do with row manipulation in the determinant basically. So just like we did manipulations here, you can do the same thing with manipulations in the determinant. And I'm going to take a look at a really easy example for n being equal to 2. Okay, what we are going to get here is nothing but, then our A looks like this. We are going to have 0, 1, 1, 0. And if we try to calculate the characteristic polynomial, this is going to look like this: negative lambda, 1, 1, negative lambda. That's a determinant, okay? And now we can just do some row manipulations in here. So that's really easy. So why not add those two together? So add the second row to the first one, leaving us with 1 minus lambda, 1 minus lambda, 1, and negative lambda. Now we have a common factor here, 1 minus lambda. We can actually factor it out. We have it on one row, so it's to the first power. So we have 1 minus lambda times the determinant of 1, 1, 1, negative lambda. And all that's now really left to do is to eliminate, for example, this one right here, meaning we are going to subtract this first row from the last one, leaving us with 1 minus lambda times the determinant of 1, 1, 0 and negative 1 plus lambda. Now here we have a common factor in this last row of negative 1 plus lambda. Let's factor it out. Let's multiply the negative in here, leaving us with lambda minus 1 times lambda plus 1. And for the general case, you are just going to go through the same procedure, so do some manipulations. I just want to do it for the 2 by 2 because it's easier to see. Times the determinant of 1, 1, 0, 1. And the determinant of this thing is just what we have on the main diagonal multiplied together, which is 1, leaving us with lambda minus 1 times lambda plus 1. And all of this must be equal to 0, meaning the eigenvalues are positive and negative 1. I hope that's clear now. Now you have to show that A is diagonalizable over Q, and you just show this by what you find out is that you are going to get an equal number of lambdas being equal to 1 and an equal number of lambdas being equal to negative 1 here. So n over 2 to the n over 2 power in each and every case. So for the main one, we are going to get the characteristic polynomial or the eigenvalues. The characteristic polynomial is going to be lambda minus 1 to the n over 2 times lambda plus 1 to the n over 2. Meaning the algebraic multiplicity of this thing here, so of each and every eigenvalue, is going to be n over 2. And now you just have to show by constructing the eigenspace that the geometric multiplicity is also n over 2, and then you are done with this. And thus it's diagonalizable over Q. Lastly, calculate the characteristic polynomial that we have here. Well, yeah, it's just what happens when you do all those manipulations, okay? So you have it as a given. And now for the last exercise, I have no freaking idea how to do this. This is why Cedric Brendel, a friend of mine, helped me figure this out. There's probably a link to this article down there in the description somewhere. Up to this day, I have no idea how to do this right here. He sent me the stuff, but I really didn't go into too much thinking about what you have to do here. So yeah, just take it as something that's extremely hard to do. I asked a lot of my colleagues, so a lot of really smart people, and none of them were able to deal with this exercise. So Cedric Brendel, you're a pretty gifted person. I give it to you, and now back to the papa for some more information. I'm very sorry for not being able to explain anything of the last exercise, but this one is really hard, and I really don't know how to do this one. So it would be really in vain to just try to explain something out of this. Just take a look at the top of the description. I'm just a normal human being. And well, it just is what it is. I do not know everything. While going over the exam, I already told you a few reasons why so many people failed. So on the one hand, most people failed because they didn't know how to deal with the matrix. And they didn't know, just like myself, know how to deal with this last exercise. Meaning half of the points you would be able to get are already completely lost because, well, you just didn't work on those exercises, and this already makes you fail pretty hard. So for the other two people, except for myself, who passed this exam, they got mostly all points here and like 1 or 2 points on this exercise, making them pass this whole thing. In my opinion, everything except for the last exercise is more than doable. This is a really easy exam, and there were way harder ones before. But in all the years where Professor, let's just call him Professor, taught at my university, this was by far the one exam with the highest failure rate out of all. And like I said before, most of the time the failure rate is extremely high, and this just has to do with the fact that the pedagogical study people have to take this exam, if you are studying also mathematics, and yeah, most of them just do not get all this abstract mathematics stuff. And if you do not work at least a tiny little bit, and if you do not practice, this abstract stuff, then you are bound to fail. But yeah, I was one of the people who actually passed this exam, and there's a pretty fun story to it. So my name Jens, okay, and there was a different one, another Jens at my university, who also participated in this exam, and he failed miserably, so just like all the other students in there. And yeah, I am pretty Gucci with most professors at my university, and then on the next day, after everything was over, Professor came to my table. We were sitting in the canteen eating something, and then he said to me, your name is Jens, right? And then I said, yeah. Why did you call or why did you send a letter to the Prüfungsamt, so like to the council basically, who manages everything that has to do with exams and stuff? And he said to me, yeah, why did you want to do a petition to redo this exam because it was way too hard, blah blah blah. And then I said to Dr. No, I didn't do this. I was one of the only people who actually passed this thing, so there's really no reason for me to redo this piece of shit. And yeah, then all of us were laughing. Also Herr Möhring was laughing pretty hard. Hello Herr Möhring, if you're watching this. And yeah, this is the story of this exam. Abstract algebra is a lot of fun. Many people fail each and every year on this exam, and I hope you did enjoy this video. As always, you can download everything down there using the links at the top of the description. If you want to see more of this, make sure to send me some exams via email, such that I can make videos out of that. Don't forget to share this video around if you did enjoy it, and up until next video, I'm wishing you guys a flammable day. Stay spicy. Ciao.